You see it, right?
Yes.
Yeah, good. Yeah, so thank you for the introduction. Thank you for the invitation to give a talk here. My name is Stefan Klein. So I'm an associate professor of medical image analysis at the Department of Radiology and Nuclear Medicine of the Erasmus Medical Center in Rotterdam, the Netherlands. And I will give a talk about data management in medical image analysis. And especially share our experiences at the Euro-BioImaging Population Imaging Node, because that's like one of the nodes of Euro-BioImaging that we at Erasmus MC are hosting. It's nice. I saw the previous talks have very different topics, so I would like to start with just a few slides on the background on the type of research we're doing in medical image analysis. So medical images. So the ones acquired at the Department of Radiology, those are MRI scans, CT scans. You've probably seen them before. Here there's some examples from the brain, heart, knee, and those images they contain a lot of information about how the patient is doing, whether there are any pathology or abnormalities going on. And typically a radiologist is looking at those images. They are I'm showing here slices, but actually they are often 3D images actually. So it's an entire volume. So the radiologist is looking at them and then learning a lot from it. But actually there's more information that you can get out of these images by using medical image analysis techniques. So you're using the computer to extract more information out of these images. For example, to make segmentation, so to draw contours around structures of interest, or to create 3D models to create a better visualization, and also to compute quantitative measures like measure the size of an organ, what's the volume of the liver, or even going directly to a kind of diagnosis, so to say something about the underlying pathology, for example, predicting if you see a tumor, what is the type of tumor, if it's a benign or malignant tumor, and what kind of specific subtype, or for example, helping in the diagnosis of establishing the diagnosis of dementia by, for example, indicating which structures in the brain are shrinking. And also we try to predict the future, let's say, trying to predict the treatment outcome or the prognosis of a patient based on all the rich information that we have in this image data. So these are some examples from radiology, but actually there are other departments that also acquire a lot of images. Here's an example from obstetrics, gynecology. So you're all familiar with this kind of ultrasound images of pregnancies. And there we can also help the doctors in analyzing these images and quantifying, for example, the development of a baby. And also in ophthalmology department, so a lot of images are taken from the eye to diagnose eye diseases. And there again, medical image analysis techniques using artificial intelligence, especially, they can help in the interpretation of these images. And with all these techniques, so I more and more they are using machine learning techniques, so that that require a lot of data to train the methods, but also then to test the methods. So we need data from multiple centers, multiple institutes to get a representative view on the variations that you in data characteristics that you encounter in practice. You need you're all probably familiar with deep learning techniques. They're very powerful, but they're known to require a lot of data. So data science, data management is becoming an important aspect in our research. Some of the challenges that we face on infrastructure to handle this data, I've listed here. So first, you need to collect the data. Okay, within your own hospital, you need to get the data out of a clinical system and prepare it for research, and also collect it from multiple institutes if you want to collaborate in multi-center studies. these images and the headers, they contain patient information, patient identifying information, yeah, simply like the name. So that needs to be removed, like the birth date. And sometimes also, for example, the image itself may be identifying. For example, in case of brain images, we see the head and you can make a rendering of the face. So sometimes we remove that as well. Data cleanup and structuring. Unfortunately, data from clinical routine often is a mess. It's not nicely organized yet, so we need to clean it up, harmonize the naming schemes, etc. We need to store all this data. It's large amount of data, maybe not as much as we saw in the previous presentation, but still, they're 3D volumes, so they can become quite big. More and more we want to share data with others, because everyone needs data, so everyone realizes we should share data with each other, but in a controlled way, in a secure way, that because it's still personal data. Even after anonymization, you have to be careful. Then we need some tools for inspection and manual annotation for training. And then, of course, the automated processing and analysis training of this machine learning algorithms. We need also high performance compute and GPUs to facilitate this. And finally, we need to integrate the imaging data with other types of data, where you're never analyzing just images. Typically, we're interested in the relation between the image data and other clinical data, or for example, genomics data. So linking it with the other data sources is also a challenge. And all of this we want to do in a traceable and reproducible way, so that if a PhD student leaves, that we can still trace back where was the data, what steps were performed on it, so that we can reproduce the previous results. So in a number of infrastructure projects, many European, I've listed here some logos, we have been working on developing infrastructure to facilitate these kind of steps, and especially Euro-BioImaging is I think the one that provides a kind of sustainable framework, because it's not a project that ends, but it's more long term basically. So that is a bit the I don't find the right word. I mean the context in which we keep on offering this kind of services and keep on developing them. And throughout the years, we have developed a kind of overall framework that summarizes a bit the infrastructure components that we typically need. So at the left, we start here with, so there's the data source. So it comes from clinical scanners or from clinical PACS systems. So that's the clinical archive for image data. Then we need to anonymize this data and send it to some research archive. And I would like to say some more about this research archive. So that's called XNAT. And that plays a major role in our data management. I won't talk about the other components in this plot, in this figure too much. So XNAT, it's an open source software. It was developed in the US in a group that's still actively developing it. And there's also an active community around it. And it provides a platform for storage, sharing, and management of medical image data in research settings. So it's open source and has an active community that is nice for it to that it's further developed based on our requests, and that there's good support. A very useful thing for us is that it imposes a kind of structure in the way you store your data. So it has a kind of data model, and it's very obvious. It's just like a hierarchy of there's different projects or different collections of studies, you can call them. Then within a project, there's a list of subjects, so the patients or volunteers. And then in each subject, there's a list of experiments. So those are the imaging sessions that this subject underwent. And then, so there could be an MRI scan, a CT scan, or you have an MRI scan at baseline and a follow-up at multiple time points. And then within each experiment, you have all the scans that resulted from that imaging session. And then, for example, in MRI, we typically acquire multiple sequences. So a T1 weighted MRI, T2 weighted MRI, so that you can nicely see them there listed under this experiment. So this, it has also an quite fine-grained access control. So each project you can make it totally public so that everyone can access it. But you can also, what we typically do is apply restricted access, so where you can see that the project is there, but you need to apply for access, or you can make it private that you cannot even see that the project is there. And then within each project, there are multiple user roles. I think also similar to what was the roles that were described in the previous talk. So there's an owner, a member role and a collaborator role. So collaborators, they only have read-only access. Members can read and edit and add data, but they cannot delete data. And owners, they can do everything, and they can also, they can read, write, and delete data, and also make new users, grant them access. It supports both DICOM and non-DICOM data. So, DICOM is the main format for storing clinical imaging data. So it's a widely established standard. But in research, typically we also, we generate some non-DICOM data. And so basically you can dump everything in XNAT. So it's quite flexible there. And you can also put an Excel file with results from image analysis there, and next to the data that it's originated from. And then what helps us a lot is that it has both a graphical user interface. So radiologists like it, so they can, who don't have programming experience, they can go there and there's a viewer, so they can look at the data, but also there's an API, so we can, via programmatic access, we can also automate all kinds of operations, and we can download the data, automatically upload data. And we actually ourselves, we developed a Python library around that API to simplify the interactions. And from the Euro-BioImaging Population Imaging Node, together with a Dutch national health research infrastructure initiative called HealthRI, we are offering an installation of this XNAT server. So so it's hosted by a professional company. So there's also regular backups of the of the data. So all that low-level maintenance we are not bothered with ourselves. So there's a help desk for the first line support, and then when there are issues, actually we step in as a second line support, and we also start updates, etc., and implement changes and fixes. And a bit about this, given the topic of this workshop, how we deal with the agreements, basically. So all users that, all institutions that use this server, they are asked to sign a data processing agreement. So that has to be done only once per institution. And we try to keep that general, and then since it's data that's typically so we only allow people to store pseudonymized data there. We don't the data should not be identifiable, but it doesn't have to be 100% anonymized. It can be pseudonymized, but given that it falls under GDPR, so it's good practice to sign this data processing agreement. To facilitate the pseudonymization, we offer a standard pipeline based on an open source clinical trial processor software that's in our community. It's often used for anonymization of DICOM data. So we can strip headers that contain a name, or replace them by a random value, for example, or by a pseudonym. And so in order to do the pseudonymization in a controlled way. So once data is has been collected in an XNAT project, the fun part starts, the processing starts. So some examples of what we can do here for brain images, we can, for example, segment the white matter, the gray matter, and the CSF, so that you can really quantify, or even smaller regions. So yeah, we have also some pipelines for analysis of knee MRI, and also we are offering some software for radiomics analysis. So where we compute a lot of features that describe the appearance of, for example, tumor, and then based on that train a machine learning model to predict some underlying characteristics and biological properties, for example, whether it's the type of the tumor. And these tools, they connect directly with XNOT, so to streamline this whole line of research. And we offer, these tools are open source, but we also offer like support in use of them. So I would like to go back a bit to the data management issue. What I described until now was really a classical central approach. So where we have one central XNOT instance, and we collect the data centrally. So from multiple centers, multiple institutes, we ask them to send the data to this place. Okay, and that's good. It's if everyone is okay with that. And then you have all the data in one place, and you can start your analysis so it becomes a central image analysis in that sense. What we are working towards, because we see there's is a bit more scalable approach, and that's based on federated analysis. So instead of having the ideas there, instead of having one central XNOT, we envision that at all the institutes, they have their own XNOT instance, so that we can assume that, okay, the data is stored in a more or less similar way. So we can make some assumptions about how the data is stored, but we don't have to store it all in one place. We don't need to maintain this monolithic big XNOT instance. And people, in a way, this feels safer for people because the data can stay within the firewall of their hospital. That gives a bit more control. But then, of course, we need to instead of doing the analysis on the data centrally, we need to turn it around. We need to send the algorithm to the institutes. So we need to do a kind of federated image analysis where we instead of bringing the data to the algorithm, we bring the algorithm to the data. And that is technically, somewhat more challenging. But if it works, then in the end, it is more scalable. Some challenges are, of course, that in a way, as an algorithm developer, you are working in a kind of blind way on the data. So you really have to, this puts higher requirements on the data harmonization. You really have to make some assumptions on how the data is stored. So there, the XNOT platform helps us. Also, another challenge that people may forget, that this puts higher requirements for the local IT services, because every hospital has to install this XNOT service and also install the analysis tools to do this federated analysis. So you need help of local IT people typically, and also paradoxically, it also brings up new security issues. At first sight, people, you could think, oh, this is more safe, because the data is not leaving the hospital. It's you don't have to collect it in a central place. It stays within our own firewall. But then what happens is someone will send you an algorithm and say, please run the software. So this algorithm could, of course, theoretically contain all kinds of viruses. You need to run some piece of code in your own infrastructure. So that again, requires some help of IT people to make sure that these algorithms are run in a safe environment, where that does not have access to the rest of the entire hospital, and that there's a way of checking this code somehow. So there's some challenges there, but we are not the first one to work on this. I mean, there's many groups in the world that have shown successful federated analysis studies. And I think the field is moving in this direction, that And I believe actually in the end we'll move to a kind of hybrid situation that for some studies where it's okay, we gather the data in a central place, and then for larger studies we support also this kind of federated analysis infrastructure. Yes, so this concludes my talk. If there's any questions, I'm happy to answer them. You can also always send an email if you are interested. Thank you.
Okay.